In part 2 of our Algebra 2 practice final, we're going to be covering questions 9 through 16, so let's go ahead and get started. So this problem is asking us which expression is not a solution to this equation. Make sure you pay attention to this not right here, unlike a particular tutor who you may be listening to right now. With this one, we want to know what's not a solution. So let's go through. First off, let's figure out what these solutions are. When you see this right here, we have to, 2 to the t, our variable that we care about is an exponent. That's a dead giveaway. We're probably going to be using logarithms. So what I like to do is I just log both sides. So I log 2 to the t equal, that's a t, log of square root of 10. Now what that does is that lets you use your property. This is all a review of your logarithmic properties. So if you don't know them, write them down. If my argument is being raised to some exponent, I can pull that out front as a coefficient. So this is the same thing as t times log of 2 is equal to log. And again, if you think about it, the square root of 10, we'll leave this for now just so you guys see it, but we're going to do something with that square root of 10 really quick. Now, if you look, t, I just have to get rid of this log 2. A lot of people struggle with this, like dividing this right here. Log of 2, log of 2, excuse me, it's just a number. That's all it is. So t is being multiplied by some number, so I just have to divide by that. Log of 2. Now here, right here, that obviously it doesn't look like an answer choice, but we have to put that in the change of base formula. What that is the same thing as me saying is if I wrote it as log of the square root of 10, base 2, I said that in the wrong order, log base 2 of root 10, that is the same exact thing as this. That's the change of base formula for logarithms. Okay, that's also something you definitely have to remember. I'm going to write that up here really quick so you see it. In case you don't remember it, that's a O. Log base A of B is equal to log of B. I can't write log of A. You've got to know that one. Yeah, it will definitely pop up. And if you don't know it, you're going to get stuck. Okay, so 2, that's good. That's a solution. That's perfectly fine. Now let's go back a bit. I'm going to take us back right here. 10, I can write that as 10 to the power of 1/2. And we can do the same thing we did up here. We can pull that 1/2 out front. So I'm just going to rewrite this really quick with the 1/2 out front times log of 10. And if we do a little bit of maneuvering, what that looks like is division by 2, or division by log of 2, excuse me. Log of 2. And if you look using your change of base formula, that's the same thing right here as saying log base 2 of 10 with the 1/2 out front. And that's number 1. So number 1 is the solution. So that can't be our answer either. And then if we look, this one's a little bit less obvious, but what I'm going to do is what I want you to remember, this 1/2 is actually, you could write it like this. You could put the 2 on the bottom. Okay, because it's 1. Now I'll leave that to you to kind of, you can do your complex fractions, but I want you to know the 1/2 is the same thing as, in this case, putting the 2 on the bottom. Now we go backwards. If you take this and we rewrite it, that's the same thing as log of 2 squared. If I go backwards on that power rule that we use, the power property of logs, 2 squared, that's just 4. And if you look, if I rewrite it, I'm just going to get rid of all this stuff. It kind of looks kind of like a whole bunch of stuff is going on. We get this, and if you notice again, we can't see this out of the screen, sorry. If we use our change of base formula, that's just log base 4 of 10. So that's also a solution, so that wouldn't be our answer. This is the only one. They literally just flip number 3 around to try and trick you. If you had a calculator, you could absolutely plug these values in. It wouldn't be very pretty, but you could do it using this formula up here to get the actual value of the logarithms to see what works, but I don't want you to have to plug those in. I want you to be comfortable knowing these properties because they could come up on a free response, and you need to know them anyway. You definitely need to know that the power rule that we did up here where we did, we pulled the t out front, where we pulled this 1/2, that's a square root, pull that out front. You got to know that. That's one of the most important ones. But this, just as important, if not more so, is the change of base formula. So this video is getting long. I apologize, but logarithms are just one of those algebra 2 things that are probably the most difficult when you see them. You're like, what in the world is this? And there's a lot of properties to remember with them. So I'm sure we'll see something with logs again. So when I take a look at number 10, it looks like we're trying to get rid of a square root right here. That's probably going to be our first step so that we can solve this for x. So if I square both sides to get rid of that square root, I end up with this. Now that's something you should be comfortable with. If we see a square root, we have to get rid of that because our x is kind of trapped inside of it. Now this looks very similar to the quadratics that we used to solve, but we can't really solve it like this. We have to get everything on the same side so that one side is equal to 0. So I'm going to subtract 3x and then subtract 40, and then we get equals 0. Now this looks way back in the day in Algebra 1 when you first were solving these quadratics, so we need to factor this. That's the whole reason I got everything on one side, so that we could try and factor it. If not, we'd have to do the quadratic formula. But it turns out that this actually does factor, so take a second and try it. But you should end up with x minus 8 times x plus 5. I was going to put 3. X plus 5. That's a 5, by the way, equals 0. If we solve these, remember all we do now is we set them both equal to 0. X minus 8 equals 0. That gives us a positive 8. This gives us a negative 5. Now, if you notice, positive 8 and negative 5, it's tempting to be like, okay, here we go, like right there. But you've got to check your answers. You have to double check and make sure that they're right for this, because when we square both sides, we could introduce a false solution. Okay, so let's double check. If I plug in 8 into our original equation, I get the square root of, this is 24 plus 40. And 8 is definitely equal to the square root of 64. So 8 checks out. We know that's right. So 3, that can't be right. 4 definitely can't be right, because we know 8 is part of the solution set because it's a solution. So if I plug in negative 5, one thing I'll get into in a second real quick, but if I plug in negative 5 inside, I get negative 15 plus 40, which gives me 25. But if I simplify this, the square root of 25 is positive 5. I get this right here. So that doesn't work. That's what I meant when your square root, when you square, it could introduce the possibility of a false solution. So just be careful. You have to double check your answers on these ones. So it's only going to be 8 is the only part of our solution set for number 10. So it looks like for this one, we're trying to find a conditional probability. We want to know what's the probability of a randomly selected person being male, given that that person is a lefty. Really what we're doing is they're telling us, okay, don't look at anything that's not left-handed. They have to be left-handed. And then given that they're left-handed, what's the probability that they're male? So our sample space is going to be all the left-handed people, which in this case is only 24. And that's a 4. Of those 24, how many of them are male? And it looks like this would be 13 to me. There's 13 males who are left-handed. So given the fact that there's the person is left-handed, that tells us that's our sample space. Of that, how many are left-handed? So 13 out of 24 is where we go with this one. So that's our conditional probability when we're doing tables. Figure out what the condition is. That's going to be your denominator. And then, figure out what's the special case. If it was females, we'd put 11 up here, right? And that's it. So we're given a function that represents the temperature of a cup in degrees Fahrenheit after X minutes. We have to find the average rate of change of the temperature. So that's basically what we're doing for this. Really what I want you to remember is the average rate of change formula. And it really looks like your slope formula. F of B minus F of A all over B minus A. Where these A and B values, these are your X coordinates of your interval. Usually your interval, actually, let me write that again. That's not the right way. The interval in this case would be from A to B. Okay, in this case, we're going from 0 to 6. So if we plug that in here, what we're really looking for is, let me change the color on this. We're looking for f of 6, and we're going to subtract whatever f of 0 is, all over 6 minus 0. So your task is to find out what this function is if we evaluate it at 6, and to find out what the function is when we evaluate it at 0, and to plug those two values in down here. Now, I had to use my calculator. Obviously, we all have to. We have this crazy looking exponent, 0.86 to the 6 times 90 plus 69. And you do all your work on that. Actually, do I have that still with me? It was like that, plus 69. It was roughly like 105. The other value, though, when we plug in 0, it was roughly, and again, this is a really, really rough estimate here. I don't have the exact values in front of me, but when we plug in 0, this just becomes 1. Anything to the raised to the 0 power is 1. 90 plus 69, that's 159. So we're subtracting these two. We get roughly negative, I think it was negative 53-ish. So down here, what we have, this is a really bad way to show you, but I expect you guys to be comfortable plugging in. This is just function notation. So we get negative 53, I believe 0.6, all divided by 6. If you plug this in with your calculator, you would get roughly negative 0.893. So negative 8.93, excuse me. And that's what we get for this one. So all this is asking us is the average rate of change is literally kind of exactly what it sounds like. How is it changing on average between these two x values? In this case, 0 and 6. And it happens to be decreasing on average on this interval, which makes sense. If you put a cup of hot chocolate out and you let it sit, it's most likely going to get colder, right? So that kind of makes sense with this one. But that's this right here. That's what you need to remember. That's the average rate of change formula for any function that you're given on this particular interval. All right, recursive formulas, really, really interesting word, but never sounds fun. But recursive basically just means that we're defining a current value in terms of a previous value. So when you see these g of n's, g sub n's, g sub 1, all that, those tell us the actual value of the sequence when n equals blank. N tells us the position. So g of 1. I want you to remember that's the first term. That's what's the value of the sequence at position 1. In this case, g of 1 is 40. Okay, so we know g of 1 equals 40, g of 1 equals 40. But the trick is, well, we're trying to find g of n. Maybe we don't know what value we want. We just want to know an overall formula for that. When it's recursive, we're going to be using a term that came before that. It doesn't have to be right before that. But what I'm getting at is, let's say I had g of 6. G of n minus 1, that'd be g of 5. And then I could put, whatever random stuff here. But that'd be recursive. That's a 6, by the way. That'd be recursive because what I'm trying to do is define a current value in terms of a previous value. That's all that recursive means, okay? So 3 and 4 are not recursive. They're not using g of n minus something, or the previous term that came before g of n. The term that came right before g of n is g of n minus 1. That's the one I showed you, g of 6 and g of 5. That's what it means to be recursive. These guys are not recursive. These are explicit formulas, and I'm sure we'll see a problem with that. But you do explicit and recursive formulas, two different things. But in this case, all you need to know for the recursive formula of this one is, one, we need to figure out what's happening. Okay, so I had to explain kind of recursive because it seems weird when you hear it, and this notation definitely doesn't help. But let's check this one right here. If this was true, what this is saying is, all right, well, if I want to find the current term, I'm going to take the term that came right before it, and I'm going to subtract 10. Okay, so what that means is, if I want to find this term, what I'm going to do is look to the term that came right before it, and I'm going to subtract 10. And it does work in this case for the first problem. It's like, oh wait, 40 minus 10, that's 30. But look at the next problem. What I have to do to find this value is, again, according to number 2, if that was true, I would look at the previous term, which is 30, and subtract 10. But that would give us 20. That means this would have to be 20 if this equation was true. Okay, so that can't be it. So that's gone. Now, by process of elimination, we got this, but I want you to know why it is the case. What happens is we start with 40 every single time that we go through the next term. Let's say I wanted 30. I would have to take the previous term and multiply it by 3/4. Okay, now that might not be so obvious, but 40 times 3/4, the 4's cancel out nicely. We get 10 times 3, that's 30. So it works for the first one, but again, remember what I say, just because it works for the first two doesn't mean it works for everything. Let's double check with this ugly looking decimal here. So if it works, what it means is I take the previous term, 30, and multiply it by 3/4. This happens to be 90 divided by 4, and dividing by 4 is nice if you just do it division by 2 twice. That rhymed, that was random. But anyway, 90 divided by 4 is the same thing as 90 divided by 2, which is 45, divided by 2 again, which is 22.5. And that's it. So really, again, all you have to figure out here is if it's recursive, you need to see this little like g sub, n minus 1 or n minus 2. Not up here. It has to be like the g, it has to be a sub, not sub, what is it? I can't even think of the word. Subscript. Oh my goodness. It has to be a subscript. So like n minus 1 or g of n minus 2. That's a dead giveaway. That's a recursive. If you don't see that, g of n minus 1 or f of n minus 1 or n minus 2, it's not recursive. Okay. It just isn't recursive. That's what recursive means. Whew. All right. That's all for that one. Okay. So we've got a little bit of statistics going on here. looking at this particular problem, again, going through, assuming that you guys have already tried this one, what I want you to see is based on this 24, if you look at this particular problem where it's saying, basically it's all about the blue candies. How many are blue? They claim that 45% are blue. So if that was true, generally 45%, I think was roughly like 29.25 of each of the bags of candies would be blue. Obviously, that's not what Bonnie got. She got a little bit less than that. So what's tempting is like, well, the company's not meeting their production standard. No, that's not true. One bag that's a little bit less or a little bit greater, especially if they're making millions of bags of candy, that's not going to make a dent at all in their production standard. The bag was a rarity. We're going to come back to this one because that rarity, what they really are trying to say is that's an outlier, and I'm going to show you guys what they mean by an outlier. The company should change their claim to 37% blue candies are produced. No. That's what they did here is they took the 24. You guys probably did this. They took the 24, divided it by the sample size that everything comes in 65, roughly bags of candy. No, bags per candy, and you get roughly 37%, but I wouldn't change my claim because, again, it's only one bag out of possibly millions of bags. So they give you these fatalistic claims, like hyperbolic claims, like, oh, they got to do this, you got to do that. But remember, it's only one instance out of possibly, millions. So that cuts it down to really 50%. Now we've got to do a little bit of statistics. I can't say the word statistics. And it really looks like we're trying to use the normal curve here. So I'm going to show you guys this, especially because this last one, within the middle 95%, I'm going to show you guys how we can find that. They give us a mean right here. So the mean is right in the middle of all of our, this right here, this all of our data points right here. The standard deviation is 3.936. Okay, so one thing that you have to remember, the standard deviation right here, let me go to the right as well. Two standard deviations to the left and to the right of the mean holds 95% of all the data points. Okay, so what we have to figure out is, does our value, what was it? Does Bonnie's value of 24 candies lie within this range? So what we do is I'll take away one. So I'll take away one standard deviation because we're going to the left. We're less than so I'm not going to worry about the right values. So if I go one standard deviation beneath our mean, I think the value that we got, what was it? I have it on my calculator here somewhere. It was 25.334. I'm just going to simplify that to 25.3. So it's not there, but the next one right beneath that, we get 21.398. This is a bad drawing right here. 21.398. So somewhere, and that's where this is. So any data that lies in between that and whatever the opposite would be over here lies within the middle 95%. And it just so happens that 24 definitely lies, after 21. It's definitely in between those values. It'd be somewhere right here, right? So it's within the middle 95%. But just so you know why number 2 is not right, because they're basically saying like, hey, Bonnie's bag was an outlier in this situation. An outlier occurs at 3 standard deviations away from the mean in either direction. Okay, so be careful with that one. What you do need to remember, this, I think they still call it this, but it was, if I'm not mistaken, like the 68, 95, 99, I think maybe 99.5. I always forget myself on that last one. But basically, 68% of your data lies within 1 standard deviation, 95% lies within 2, and then this, I think it's 99.5. It might just be 99. I'm forgetting. You have to double check that rule. Lies within 3 standard deviations. Okay. This is definitely something that you have to remember because it makes life a lot easier and you can't do it without it. So that's all they're asking for here. We're doing a little bit of normal, the normal curve, and doing a little bit of the standard deviation. I can't even think of the word properly. Analyzing. We're just analyzing the normal curve pretty much for this one. So hopefully that made sense. So this one has a couple of values that look weird. The statistics, again, I can't say the word, kind of comes up weird in Algebra 2 at times with the wording. What I want you to see is when we're trying to figure out which technique can be used to determine if a single variable has an impact on a given population. We're talking about a particular single variable. The best way that we can do that is with a controlled experiment. A controlled experiment is just basically where you're actually, you're defining whatever, usually a control variable, but you're defining the variables and you can actually change certain variables to manipulate them and see what the outcome is on our variable of interest. A single variable, the best way that we can determine if it has an impact is by a controlled experiment because we can manipulate the variables and see what the outcome is overall. So 16 is asking us, as theta increases from negative pi over 2 to 0, what's happening to cosine? So I think the easiest way to do this is to draw a unit circle. So I'm going to try my best. Usually it autocorrects to a circle. Yeah, there we go. Unit circle just means that the radius is 1. So let's plot our points. This is not a perfect circle. But here, this would be 1, 0. Up here would be 0, 1. That's a 0. Back here would be negative 1, 0. And down here would be 0, negative 1. Negative 1. Okay. So what's happening is they're saying, okay, well, as it goes from negative pi over 2 to 0, negative pi over 2, remember, we always start at the positive x-axis. Negative pi over 2 would be me going down a quarter turn down here. So we're right here. We're right at this point. I'm going to put this in a bright, what can I do? Bright pink. Can we see that? We're right there right now. And they're saying, okay, well, as I move to this point, to 0 radians, what's happening to cosine? What you have to remember, and you've got to know this, is that when we're doing the unit circle, the x value is equal to cosine. So if you look at this right here, at negative pi over 2, our x value is 0, aka cosine is 0. And then up here, as we move, once we get to this final point, the x value is now 1. So cosine has changed from 0 to 1. Where is that? Increased from 0 to 1. That's the best way I think we can do this in Algebra 2 sense. You may have seen the graph of cosine. I don't think a lot of you do that in Algebra 2. That's more of a pre-calc thing, but you may have seen the graph. If you prefer the graph of cosine, we could draw this and say what's happening as we go from here to here. It goes from 0 to 1, same exact thing. But I think most of you would probably do the unit circle, and I want you to be comfortable with the unit circle as well, and especially this. X is cosine, y is equal to sine of theta. Okay, those are two really important things for these trig problems that you have in Algebra 2. All right, so that is it for part 2 of our Algebra 2 final review. Make sure you like, subscribe, and share this video to help others, and we'll see you in the next one.